Okay, in this video, we are going to do 7 topics that I think everybody could use a quick refresher on before they take their AP exams. And then I have an 8th kind of page that's just a lot of BC specific things. So let's take a look at the first one, which is the limit definition of the derivative, right? Calculus is derivatives and integrals. This is kind of half of it. So you want to remember, maybe you haven't looked at it in a while, the limit definition, f prime of x. Limit as h approaches 0, f of x plus h minus f of x all over h. Alternatively, sometimes you'll see it evaluated at a particular point, or you'll see this alternate definition. So f prime of a is limit as x approaches a, f of x minus f of a over x minus a. In the multiple choice, a lot of the limits that you see are actually the limit definition of the derivative. You definitely want to recognize that. Now, with this second one in mind, where you're getting a value of the derivative, it's really common for them to just take a value of a and sub it into that first one. So you'll also see this from time to time. Now, on free response questions, you're often going to want to, well, not often, but sometimes they ask you to use one-sided limits, in which case you will be looking at the limit as x approaches a from the left of f of x minus f of a over x minus a, and you're going to compare it to the limit as x approaches a from the right of f of x minus f of a over x minus a. In the past, when this has been on the exam, one of these will be positive, the other one will be negative, and therefore they cannot be equal if you're trying to show that something is not differentiable at a point. Now, what that would look like graphically is maybe something like this. If you're not told to use one-sided limits, every year in the past, it's been acceptable to say the function is not differentiable here because the graph has a sharp turn. On the other hand, I think that this limit from the left, limit from the right thing, much better answer. So if you're going for like 100 on this exam, you definitely want to know that. Another thing to keep in mind with the definition of the derivative is not exactly the definition, but beware the symmetric difference quotient. So the symmetric difference quotient is a little bit tricky. So if f is differentiable at x equals a, then the symmetric difference quotient, where instead of like just moving to the right with h, you move to the left and to the right. So limit as h approaches 0, f of a plus h minus f of a minus h all over 2a. If you're differentiable at that point, this will give you the same thing as f prime. The caveat to that is, if you are not differentiable at that point, the symmetric difference quotient can lie to you. The classic example, and the place where it mostly comes up, is the absolute value of x. The symmetric difference quotient would tell you that the value of the symmetric difference quotient at 0 is 0, but we know that the absolute value of x is not differentiable at 0. Symmetric difference will give you 0. That is not correct. So if you're not differentiable at a point, this one can lie to you. Just be on the lookout for that in those multiple choice questions where it's like, of these 3 things, which are true? It's like 1 and 2, 1 and 3, whatever. That one shows up in there sometimes. Okay, on to topic number 2, which is going to be about the chain rule. So the chain rule in multiple manifestations. So first of all, you got your standard chain rule, which is just if h of x is f of g of x, then h prime is f prime of g of x times g prime of x, right? You've seen that a million times. Another place that the chain rule comes up that sometimes people forget it, basically people just forget the chain rule, so don't forget the chain rule. The second fundamental theorem, right? So the second fundamental theorem, so that's the derivative d dx of the integral from a to f of x, g of t dt. So what you're going to do is take the upper bound and sub it into the integrand, so that gives you g of f of x, and then times the derivative of the upper bound. That's where the chain rule comes in, so times f prime of x. Don't forget that. The next place that chain rule comes up where people tend to forget it is implicit differentiation, right? So if we're going to find the derivative with respect to x of x squared y cubed plus sine of y equals 5, we're taking the derivative with respect to x of both sides, and then when we go through it, we get the derivative of x squared y cubed is, it's x squared, the derivative of y cubed is 3y squared, and then times dy dx, plus, because it's a product rule, the second, which is y cubed, times the derivative of the first, so 2x. And then when we take the derivative of sine of y, we get cosine of y times dy dx. So these are all the instances of the chain rule. So when you're doing implicit, don't forget the chain rule. I think people forget the chain rule all over the place. So watch out for those. I put them in red to try to remind you. The next place that you might see the chain rule that I think is super underrated is actually just related rates. So for example, you'll have problems that say like if g of x is measuring kilometers as a function of gallons, and x of t is gallons as a function of time, and then you're trying to find dg dt. So a hint that you're going to use the chain rule, I mean, they're really doing related rates, but a hint that this is the chain rule would be that g is a function of x, but you're being asked for dg dt. So as soon as you're being asked for the derivative of a function with respect to something that is not the independent variable for that function, chain rule problem. So in this case, you could just say dg dt is definitely dg dx, because that's all you can find there, and then times, you got to do something to get rid of that dx, which I know is not the exact proper math, but times dx dt. And that's going to give you the answer that you're looking for. I would recommend for this related rates thing, if you're really like hardcore studying right now, there are two FRQs that are like amazing related rates types problems. So it's 2008 B. There used to be a form B, just Google it. Number 2, part B, and then 2007 form B, number 3, part C. Definitely check those out if you're like really locking in right now. All right, let's take a look at the next topic. And that's going to be derivative of the inverse. So this is in like every review video that I do because it's pretty much always a multiple choice question. Sometimes it's a free response question, and it's just like too easy to get wrong. So if f and g are inverses, then the following things are true. Number 1, if the point AB is on f of x, then the point BA is on g of x, right? Because they're inverses, you switch the x's and the y's. Now the big thing to tie it all together is that derivatives are related. So f prime of a is 1 over g prime of b. So that's what we need to remember. So if AB is on f, then BA is on g. F prime of a is 1 over g prime of b, or g prime of b is 1 over f prime of a, however you want to say that. Now I have an additional tip for this because sometimes you're not just asked for the value of the slope of the inverse. Sometimes you're asked for the tangent line. Do not mess up the x and y coordinates of the tangent line. So because the point b comma a is on the graph of g, if you're writing a tangent line in point slope form, make sure that you do y minus a is 1 over, it turns out to be f prime of a. I mean, it should just be g prime of b, but we know that g prime of b is 1 over f prime of a. So 1 over f prime of a, and then the quantity x minus b. Similarly, if you're going to write the equation of the tangent line to f, don't forget that the ordered pair for f is a comma b, so you do y minus b is, it should just be f prime of a, but we know f prime of a is 1 over g prime of b, the quantity x minus a. Watch out for the x values, and also remember, in the problem that they present to you, you're always being given the x value for the inverse function, which means you're always being given the y value for the original function. So that interplay will always come in. I don't like seeing people get this wrong because it's just too easy. All right, let's take a look at the next topic, which is IVT, MVT, and EVT, the extreme value, well, rather the value theorems, right? You got intermediate value, mean value theorem, extreme value theorem. They're all important. I would say EVT is probably the lesser important. I already have a really good video on this, so I'm not going to like rehash everything. You should just check out that video. I'll put a link in the description. But here I just want to highlight the things that you need for these to work, right? So IVT is basically an algebra 2 problem, or a theorem. So IVT only needs your function to be continuous on the interval. Sometimes you need to establish that the function is continuous though, and in that case you would look to see if the function is differentiable, and you would say the function is differentiable, therefore it's continuous, therefore by IVT, etc. Now when you're talking about mean value theorem, that's very calculus based, right? So for mean value theorem, we're going to need continuous on the closed interval, and we're going to need differentiable on the open interval. For the most part, I would say, in AP Calculus, it's usually actually differentiable on the closed interval, so you kind of don't have to worry about it. But still, it's continuous closed, differentiable open. Every time you use mean value theorem on an FRQ, you better be writing that down because it justifies that you're allowed to use it. The other thing I would suggest on multiple choice more than anything else is watch out for C values that are outside of the interval from A to B. Those are not guaranteed, and so when the question says like how many values of C are guaranteed by the mean value theorem, it's only the ones between A and B. So if you have one outside of that, you just discard it for those purposes. And then finally, there's EVT, extreme value theorem. All you need is for the function to be continuous. It's another kind of like algebra 2 type of theorem. We need it to be continuous. Extreme value theorem is the least utilized. It just says that if a function is continuous on a closed interval, then it definitely, the function has an absolute maximum and an absolute minimum. It allows us to use the candidates test. It shows up in multiple choice questions frequently where it's like, which of the following must be true? And if they don't tell you that a function is differentiable, then all you might know is that it's continuous, and that's where the extreme value theorem really comes into play. All right, that's it for that topic. Let's take a look at the next topic, which is errors for sums. So when you're doing Riemann sums, when you're doing trapezoidal sums, you're sometimes going to be asked about what type of error you're getting. My recommendation really on all of these is just draw a picture. Don't overthink it. In fact, kind of don't think it at all. Just draw a picture. So if we have an increasing function, we draw it, we draw our left sum. Left sums are definitely underestimates, right? So this is what I mean by just draw it, don't think about it. And then we could have like a more interesting function. It doesn't really matter. If a function is increasing, a left Riemann sum will be an underestimate. A right Riemann sum will give you an overestimate. Now for decreasing functions, if we have a decreasing function, our left Riemann sum is going to give you an overestimate. How do you know? Because you drew a picture and you can see that your rectangles are bigger than the actual area. That's how you know you're getting an overestimate. Draw the pictures. Similarly, if we drew a right Riemann sum, it would be an underestimate. So for left and right Riemann sums, concavity does not matter at all. On the other hand, there are two other types of sums that you do. There's trapezoidal and there's midpoint sums. For those, only the concavity matters. Doesn't matter if you're increasing or decreasing. If you are concave up, a trapezoidal sum is going to give you an overestimate. And you can see in this picture, sometimes we're decreasing concave up, sometimes we're increasing concave up. No matter what, we're getting an overestimate. Now, for midpoint sums, it's kind of related to the trapezoidal sum, but basically what I do is I always think to myself, would a trapezoidal sum give an over or underestimate? Because a midpoint gives the opposite of that. So as soon as your concave up and trapezoids give overestimates, midpoints give underestimates. I don't draw a picture for that. Actually, I just draw the trapezoid sum. Midpoints always do the opposite of trapezoids. And when you're justifying, you just need to say, like, this will be an underestimate because when a curve is concave up, a midpoint sum gives an underestimate. Like, you're referencing the concavity. That's all you need to do. And then for concave down, kind of the reverse result, right? So we have a concave down function. Trapezoids are definitely underneath it. You can see that because you're going to draw a picture. And then if trapezoids are under, that means midpoints are over. And again, I think midpoint error is like by far the least tested, but it could be on there. So just remember, the midpoint is always doing the opposite of whatever the trapezoid is doing. All right, let's take a look at the next topic, which is going to be asymptotes and discontinuities. So this is almost like an Algebra 2 type of thing or a pre-calc thing, but you got to review it right before the exam. So we have horizontal asymptotes. Horizontal asymptotes are limits to positive and or negative infinity is a constant. So you have to take the limit to infinity and or negative infinity. And people forget that all the time. There's kind of a famous multiple choice question that looked very much like this one. And the question was, what are the horizontal asymptotes? And everybody took the limit to infinity and forgot the limit to negative infinity. So what we want to do here is first we got to take the limit to infinity. We get -1 when we do that. Then you also have to take the limit to negative infinity, where you will get 3/5. You're getting two different answers. There's two different horizontal asymptotes. So do not forget, you got to go to positive and negative infinity. Rational functions mess us all up because rational functions will only have one horizontal asymptote, so we all get lazy about it. But just remember, you got to go to positive and negative infinity. The next thing I would mention here is for horizontal asymptotes, if it's possible to just L'Hopital's your way to 0, then y equals 0 will be a horizontal asymptote. So for example, if you have y equals x to the 500 over e to the x, if you apply L'Hopital's rule like 500 times, or maybe 501, whichever it is, eventually the derivative of the numerator goes to 0. The denominator is always just e to the x. Eventually you will get 0. So if you can L'Hopital's your way to 0, y equals 0 will be a horizontal asymptote. This shows up sometimes in the multiple choice where it's like, which of the following functions has a horizontal asymptote or whatever? And it's like, you're not going to do the work on that. You're just going to look at it and be like, well, an exponential is going to beat a polynomial. So that would definitely work out. All right, so horizontal asymptotes covered. Vertical asymptotes are as you approach a particular value, you either get positive or negative infinity. The thing that I think that most people think of, and it's totally valid, is that usually these are just going to be the zeros of the denominator that do not cancel out. And that's how I usually do them, because often these are just like rational functions that you're looking for. I don't have much more to say about that. Let's talk about holes and or removable discontinuities, whichever one they choose to use. So what you need to look for a hole or removable discontinuity is it's going to be a factor that totally cancels, right? So if you have like x plus 2 over x plus 2, that cancels. There's a hole at -2. Or it stays in the numerator after you cancel. That's the weirder one, and I think it generally speaking doesn't come up on the exam, but I wanted you to be aware of it. And then also the definition, the actual definition is the limit as x approaches c of f of x exists, but is not equal to f of c. So maybe f of c exists, maybe it doesn't matter. The limit does exist and is finite and doesn't equal the value of the function. Here's a function to just kind of look at, right? So this has that behavior I was talking about. So we can cancel the x minus 3 in the denominator, but it leaves an x minus 3 in the numerator, which means there's a hole at x equals 3. And then there's obviously a vertical asymptote at -5 because that's a 0 the denominator that didn't cancel. So sometimes they ask about that. Feels very pre-calc, but whatever. Also, there's a jump discontinuity. I don't know. They don't ask about, like, is this a jump or... Well, I mean, I guess sometimes they do. Multiple choice for sure. So a jump discontinuity, the limit from the left exists and is finite. The limit from the right exists and is finite, but they are not the same number. So jumps are easy to visually identify, I think. So that does it for this topic. Let's take a look at the next topic, which is volumes. So when we're talking about volumes, I'm talking about kind of like 3 different things. Volumes of revolution around horizontal lines, around vertical lines, and then volumes by cross sections. First, we're going to look at horizontal lines. So keep in mind the x-axis is a horizontal line. It has the equation y equals 0, or it could be y equals 5, y equals -10, etc. I'm going to draw 3 different pictures and show you how I go about doing these. I think of volumes around the x-axis as being like the normal volume, like everything is in terms of x and everything behaves the way you kind of want it to. So our first picture could look like this, and we're just going around the x-axis. I forgot to put in the arrows, but that's okay. What I always do is I find a big R and a little r, and in this case, because you're doing dx, you're going around a horizontal line, it's always the top minus the bottom. So big R, in this case, is just f of x minus 0. Like one of those 2 segments I drew is bigger than the other. That's big R. So big R is f of x minus 0, and then little r is g of x minus 0, and then our volume is pi, the integral from a to b of big R squared minus little r squared dr. Now, we can have a different picture which popped up instantaneously, where instead of going around the x-axis, we're going around y equals k. This doesn't change anything. We're still going to find big R and little r. They're just going to feel a little different, right? So we draw them. One of them is bigger than the other. That's big R. That's going to be f of x minus k, top take away bottom. Little r, g of x minus k. That's top take away bottom. And then our integral is exactly the same. Now there's a third scenario, which is really no different, where the axis we're going around is above the region, right? But we just draw things. You can see the color has changed because the farther out curve is different this time, but you still just draw those 2 segments, whichever is bigger is big R. Big R is going to be k minus g of x, that's top take away bottom, and then little r is k minus f of x, top take away bottom, and then our integral is exactly the same, pi, the integral from a to b, r squared minus big R squared minus little r squared, and then dx. Okay, so for these, you're always just doing pi, the integral, big R squared minus little r squared, and then dx. But actually, the idea is exactly the same when you do this dy. Let's take a look at that. So everything here has to be in terms of y, right? So if you're going around the x-axis, it's like normal. If you're going around something parallel to the x-axis, it feels normal. If you're going around something that is the y-axis or parallel to the y-axis, like x equals 5, x equals -6, everything feels weird because everything is y values. The bounds are y values. The functions are functions of y. You write dy. Let's look at the pictures. The process doesn't change, right? We just draw our segments. One is bigger than the other. That's big R. And in this case, you're always doing right take away left. So when we do right take away left, first big R is f of y minus 0. Little r is g of y minus 0. And then our integral, everything is in terms of y, so I'm going to really highlight that here. We have pi, the integral from y equals a to y equals b, and then it's big R squared minus little r squared, and then dy. If you write dy, everything needs to be a y value. The functions are functions of y, the bounds are y values, just everything is y. We could go around a different axis, so we're going to be to the left of the y-axis, right? We have a big R, we have a little r, I already drew them in accidentally. Big R is right take away left, so f of y minus k. Little r is right take away left, g of y minus k. And then our integral is exactly the same, right? It's pi, the integral from y equals a to y equals b of big R squared minus little r squared dy. So just keep that in mind. We have one final option here where the axis is to the right of the region. So we have this. Again, we draw. We have a big R and a little r. They've changed colors because that's just what happened. It doesn't matter whichever one is bigger is big R. So in this case, we're doing right take away left. You're always doing right take away left. So big R is k minus g of y. Little r is k minus f of y. Our integral is exactly the same. So we just get that integral again. I'm not going to read it again. And then for volume, we have yet another option. And that could be volumes by cross sections, right? So for volume by cross sections, I didn't label this number 1. It's weird because I label everything else. But you have a region. So the weird thing about volume by cross sections is that the region itself kind of doesn't matter. You need where the region starts and where the region stops. So you could have a top takeaway bottom type situation. That's going to be dx. You could have a right takeaway left type of situation. That's going to be dy. Remember, dx, everything is x values. dy, everything is y values. The dx type always feels a little more normal. So what you're going to do is you're going to calculate something that I call S. So we're going to find S. And it's either top takeaway bottom or it's right takeaway left. So there you go. So that idea just permeates everything when you're doing these. Now, what we need to do is find the area of the cross section that they stipulate. They will just tell you it's going to be squares. The area of a square is s squared. It could be rectangles. Rectangles are the most contentious kind of because I tend to say that they're just k times s squared because usually they say the height is 5 times the base or the height is 52 times the base. But they might also just tell you what to do. Like the height is always 6, so then it would be 6 times s. Or the height is always, I don't know, x cubed plus 15, so it's x cubed plus 15 times s. So whatever they tell you is what you go with. Semicircles, well worth memorizing. It's pi over 8 s squared. Equilateral triangles, well worth memorizing. Root 3 over 4 s squared. And then the weirdest thing they can do is they'll just give you a formula. They'll be like, the area of a cross section is, I don't know, recently they did like 1 over x plus 5, right? And so you're just integrating 1 over x plus 5. The volume that you're going to find is always, very easily, the integral of the area of the cross section. That's it. So the bounds that you use, if it's dx, you go from the leftmost point to the rightmost point. If it's dy, you go from the bottommost to the topmost. Remember, everything is y if it's dy, everything is x if it's dx. I would suggest if you're looking for some weird problems, look at 2008, number 1, parts C and D, in particular D on that. And then in 2019, number 5B, that's like 3 representative type of problems of kind of everything I just talked about there. All right, that's all I got for AB. I'm going to move on and talk about some quick hits on BC stuff that people make mistakes on. So let's take a look at that. Okay, so the BC only stuff. Mostly just going to tell you what not to screw up here. So first thing, Euler's method. Don't forget the delta x. I see people do that all the time. Also, if it's free response, don't forget at the end to say that the value you're approximating is approximately the value that you just calculated. Those are the 2 biggest mistakes I see people make. Don't do those. The next thing, Taylor series. Don't forget the center. So it's always the quantity x minus a to the n. I see people forget that all the time. Tragedy. The next thing, improper integrals. The notation matters a ton. This is for free response questions, basically. So if you start off with the integral from 3 to infinity, you better change that into the limit as b approaches infinity of the integral from 3 to b before you do your fundamental theorem stuff. So the notation really matters. You will lose a point if you do not do that. Also, I forgot to write it down here. There's no such thing as symmetric divergence. So if you have to split your improper integral in the middle, like you do the integral from 0 to 2 and 2 to 5, if the integral from 0 to 2 diverges, just stop. You're done. As soon as one part diverges, the overall thing diverges. That was on a recent AP exam. Off the top of my head, I don't remember which. but make sure you're aware of that. The next thing I see people screw up, polar area. Don't forget the 1/2. Also, I guess don't forget that it's r squared, but in particular, I see people forget the 1/2 more often. So it's 1/2 the integral from a to b of r squared d theta. So don't forget that. The next thing I have for you, logistic differential equation. Just memorize it. Dy dx is k times y, the quantity 1 minus y over L. That 1 really matters. You have to have it look exactly like that. When it looks like that, the limit to infinity is L. The point of inflection is L over 2. That's really the two questions that they will primarily ask you about it. They might ask you about the range of a differential equation, of logistic differential equation. I think that's valid. So if you start below the limit, then it's like where you start, including where you start, up to the limit. If you start above the limit, then it's where you start, including where you start. Well, no, it's actually the limit, not including the limit, up to where you start, including where you start. Basically, just never include the limit because you never get there. And then the last thing that I see people commonly do that's like really easily avoidable is when you're doing arc length perimeter questions, which I know is like not going to come up 100% of the time, but it might. Don't forget the horizontal and the vertical segments, right? So I've drawn a little picture here. Most people, when they do this, they'll either forget that length along the x-axis, the length along the y-axis, or that vertical segment that goes from the x-axis up to that one point, right? So don't forget those. It's like you get so excited to use the arc length formula that you then just forget that you can easily find horizontal and vertical things. Those are the most common, like really simple things that I see people losing points for. And that's the whole video. So I hope this was helpful and good luck.